Okay. Well, we are going to get started here. Thank you guys so much for coming. I hope you guys had a good show and we can wrap this up in a bang. My name is Don Barnettson. I'm VP of Product at Credo, and I'm representing the Data Center Rack and Network Interconnect booth, which is right over there by the other side of the Experience Center. So we put together a group of 12 companies to get you guys a sense of how Data Center Rack and Interconnect is proceeding today and how it's going to evolve over the next 3 years. And if you have any time left in your show and anything left in your feet, please come over and take a look before the show wraps up at 2 o'clock. A quick note from my legal department, please make sure you read every single word. So AI has really challenged data center infrastructure in an unprecedented way. So we're seeing power densities are increasing just wildly. We've been sort of running in a world of 8 to 12 kilowatts per rack for many, many years, and very rapidly we're moving up to 50 kilowatts. 50 kilowatts requires us to go to either very advanced air cooling with sealed plenums, or as you'll see in the booth, lots of different liquid cooling options with cold plates on top of the key chips inside of the devices. This is a major impact, not just to infrastructure, but also to serviceability. Meta has an excellent demo talking about how they're actually going to service some of these liquid cool things in the booth. Please take a look at that. On the networking side, which is much closer to my heart, things are changing, frankly, even faster. So we've been building racks that have 1 to 2 terabits of capacity in them for a single front-end network. Suddenly we're going to AI, we're adding an entirely separate back-end scale-out network that's 5, 10, sometimes 20 times as large as the network that we have been building towards. Absolutely amazing. It needs to be lossless, it needs to be low latency, it needs to be very low jitter. It has elephant flows, which is historically not something we've dealt with, where suddenly you go from 0 utilization to max port utilization instantaneously. There's very little you can do, especially in a lossless environment, to manage that. And you're not getting very much entropy for the traditional load manager or load balancing structures like ECMP that we've used. Very, very difficult to put together, very challenging. So what we built in the booth is on the left-hand side, you can see we've got 3 meta demos. We have their blind mate rack, which allows you to slide a server rack right into a chassis, and the liquid connectors blind mate at the back. They bleed themselves, and auto-magically you've got liquid flowing to your high-temperature things. Have a look at that, super cool. We've got the liquid servicing or liquid cooling service cart. You can kind of think of it as an oil change cart for your liquid cooling. How are you going to drain all of this liquid into something in order to service this device? In that case, it's a heat exchanger on the back of the rack that they're showing as an example. Meta also uses an autonomous tug and cart system to move racks around their data center. So there is an entire autonomous tug and cart system over there. It's a whole lot better than pushing 2,000-pound racks bit by bit, 3/4 of a mile out to the data center. Very, very cool thing, nifty to see. On the right-hand side, we've got Flax that's showing equipment or heat reuse and equipment recertification. Maybe you have a colo site and you actually can use the heat for something rather than just having to dump that. And maybe actually power is becoming the constraint in lots of cases, so let's use that power and that waste heat for something good. WeWin showing a liquid cooling demo, which I'd encourage you to look at, and then UfiSpace is showing some of their network switching hardware. Across the back, Credo's worked with a variety of partners to build an entire data center. From an interconnect standpoint, a view of 2024, how data centers are built today, and how they might evolve in 2027. So if you look on the left side, we've got 3 racks of general computing. The very left is an existing rack of Meta Yosemite servers, a single front-end network going to a leaf rack in the middle. Pretty straightforward, but that's very much how things are built today. Next to that, with the blue cables, we believe that rack scale interconnect wants to evolve to CXL in order to avoid having DRAM being stranded in these boxes, and then to centralize the DPU, the data processing unit, the very expensive NIC card that we're evolving towards, into a single TOR. So this allows us to recover that very expensive stranded DRAM, to get higher utilization on that very expensive DPU, and to make a much more efficient general compute rack. On the right-hand side, we've got AI land. So the first rack, the silver boxes that you see here, are Intel Gaudi 2 servers. They have 2 networks. They have a front-end network that's about 400 gigabits of capacity, but then they have a back-end network to facilitate managing these large workloads, which is 2.4 terabits of capacity in an existing server. It's about 5 times as much capacity per box. Those come together in two different air gap networks. So we have a front-end network which connects to the spine in the middle, just like general compute does. That's how things come in and get out of here. But we have a back-end network that allows us to work on these very large models that simply can't be done on a single chip, a single box, or even a single rack. We need an entire row or sometimes many rows to collaborate across these models to achieve what we need to do, both on the training side, but in this case, more so on the inference side. All the way on the right-hand side, we have a 2027 AI rack. We believe that that back-end network very much wants to evolve towards CXL, because CXL is a guaranteed lossless network. It's an open standard. It's about an order of magnitude lower latency than the big buffer Ethernet that we have running the 2024 network. And it has power modes. Power is going to become very, very important to us. So a user space application can actually say, you know, I don't really need this network for the next 20 microseconds. How about you shut down and save me 85% of my power? And then you can snap right back up and keep going. Can't do that with Ethernet, definitely can't do that with InfiniBand. In support of that CXL, Credo announced the Highwire CXL Consortium at the show here. So we're partnering together with approximately 30 of leading companies in the space to standardize CXL or PCI Express-based active electrical cables in order to support these rack-scale interconnects. We announced that early this week, and we're going to have our first meetings in the coming week. So if you're interested in that, come talk to me. We think it's very, very important that we standardize this. If you're familiar with the Highwire Consortium, we started it back in 2019 to standardize Ethernet active electrical cables, and it's now become the basis of the active electrical cables that run many of the hyperscalers' Ethernet networks today. We think we see the same opportunity in CXL, although at a much denser network because we're doing many more functions than we did with Ethernet. Second important product is our pluggable patch panel, the Credo Highwire P3 Box. You can think of this as a box. It's a switch without a switch. So if you're familiar with patch panels, they tend to be passive devices for optics or maybe for RJ45 copper. In this case, we're building it for pluggables. So if you look at that row, you can use an active electrical cable in order to remote an optic off the surface of your switch or router. Inside of the P3, we're actually making a direct electrical connection between the AEC and the optic. And you might ask me, why on earth would I want to do that? Why not just plug the optic straight into the front of my router? Well, it turns out that some of the new optics don't work so well in the routers. Maybe the router doesn't have enough power or cooling to drive a modern coherent optic. Maybe the router doesn't have software compatibility, or there's licensing issues that don't allow you to plug it in. But more importantly for some of our customers, maybe the speed of the optics is totally different from their core speed. So a lot of the MSOs now are moving to a 400 gig core network, but they're still looking to use 100 gig long reach optics, ZR or LRO4 type optics for their distribution network. If you plug a 100 gig optic into a 400 gig port, you just dumbed it down by 3/4. That's not economic when some of those ports cost you $2,000 each and up. So the P3 is a very simple device that bridges and solves that problem. So my call to action, you don't have much time left in the show. I've probably seen everything else. Come over to the Experience Center, talk to me, talk to the other companies that are exhibiting there, learn about liquid cooling, heat reuse, autonomous maintenance, and close to my heart, the future of Interconnect. Also, consider getting involved with OCP. OCP isn't just this show, OCP is everything that happens behind the scenes to create all of these open standards that we build this entire ecosystem on. That's it, thank you so much. If you guys have any questions, come see me. Cheers, guys.